Welcome back to Chapter 4. In this Section 3, we're going to be looking at connecting the derivative and the second derivative to the graph of the function. Like, what do they mean? A lot of this stuff, especially with the first derivative, we have already covered a few times, including in the past couple sections. The second derivative we haven't talked too much about yet, other than it's the change of velocity, so it's the acceleration. But what does that mean with the graph? So we're going to see that, and then we're just going to kind of wrap it all up at the end. So our learning targets, we can use the first derivative test to determine local extrema of functions. Use the first derivative to determine local extrema of functions. We just did that. The test is just saying that, hey, this is what it is. Use a concavity test to determine where functions are concave up or concave down. That's new. That'll be second derivative stuff. Find points of inflection of functions. Again, that's second derivative. Use graphs to determine characteristics of a function's derivatives and antiderivatives. And then find velocity and acceleration of particles in motion. So, and we've done that in previous chapters. Like, there's not a whole lot new in this section. These are big topics, and so it's nice to hit them a couple times. So, the first derivative test for local extrema, here's a graph, and so our local extremes, we have our local maximum, we have an absolute maximum, we have a local minimum here, then we have an absolute max and a low, or absolute min and a local min. And so these are, as we notice, when f prime equals 0, or f prime is undefined, or at the endpoints, just like we saw before. And so the first derivative test just says, at a critical point, if the derivative changes from positive to negative, you have a maximum. Number 2, if the derivative changes from negative to positive, you have a minimum. And then 3, if the derivative does not change, then it's neither a maximum nor a minimum. And we actually see that a couple places here. We see here the derivative is 0, but it's negative on both sides. Here the derivative is 0 and it's positive on both sides. It's not just where the derivative is 0. The derivative has to change signs, and it can do that when the derivative is 0 or when the derivative is undefined, or if there's a discontinuity as well. But this is specifically for a continuous function. So we have when derivatives are 0 or undefined, and then also the endpoints. At the left endpoint, that would be this one over here, it's a maximum if the derivative is negative, because it starts out and then the derivative being negative means it goes down from there, which makes it a maximum. It's a minimum if the derivative is positive right after that. And then at the right endpoint, it's a minimum if the derivative is negative because it's dropping to that. And it's a maximum if the derivative is positive because it's rising to that. So that's the first derivative test for local extrema. It's no different than what we've already been doing finding the extreme values. So let's look at one. So we have f of x is x cubed minus 12x minus 5, which means the derivative, and this is continuous, so we don't have to worry about that. The derivative is 3x squared minus 12. All right, we want to know when the derivative equals 0. It'll never be undefined. 3x squared minus 12 is defined everywhere, so we don't have any corners or cusps or anything like that. So we can factor out a 3. Now we get x squared minus 4, which means we could have 3 and x plus 2, x minus 2, and so x could equal 2 or negative 2. So we'd make our sign chart. We have negative 2, we have 2. Our derivative is 0 at those places. Then we need to know what is it doing in between. So if we plug in a number less than -2, and we can plug it right into this factored part of the derivative, if we plug in, say, -5, we're going to have 3 is not going to change anything. -5 plus 2 is a negative number. -5 minus 2 is a negative number. Negative times the negative is a positive. So the derivative is positive there. And then we can plug in a number in the middle, like 0. 2 times -2 is a positive times a negative, which is a negative. So it's negative there, which means that this, at x equals -2, we have a maximum. It'll be a local maximum because a cubic function we know is going to go like this, and it's going to go off to infinity. So there won't be an absolute maximum. But at x equals -2, we have a maximum. And then, so we plugged it in for 0. Now something bigger than 2, like 5. 5 plus 2 is positive. 5 minus 2 is positive. Positive times a positive is positive. Since we're going from a negative to a positive, that means that there is a minimum at x equals 2, which also the little sketch of a cubic graph that I drew shows that as well. How about a different one? G of x equals x squared minus 3 times e to the x. Ooh, we have a product rule here. So u will be x squared minus 3. V is e to the x. So dv is e to the x. du is 2x. So our g prime of x is going to be x squared minus 3 times e to the x plus 2x times e to the x. We can factor this because we're going to have to make this equal to 0, figure out where we're looking at. So we can factor out an e to the x, leaving us with x squared minus 3 plus 2x, which we can factor. That's x squared plus 2x minus 3. So we have x plus 3, x minus 1, because 3x times negative or plus -1x is 2x, and yep, multiplies. So here we need this to equal 0. So we have x equals -3, x equals 1, and e to the x. E to the x, how is that going to equal 0? Well, that's not going to equal 0. E to the x will always be positive. It has an asymptote at 0. It'll get closer and closer to 0 when x is going to negative infinity, but it will never equal 0, so we don't have to worry about that. So we can make our sign table. We have -3, and we have 1. So f prime, it's 0 at these two. We can plug in values of something less than -3. Again, e to the x will always be positive. It will not affect the sign. So something less than -3, we have a negative times another negative, so that'll be a positive. Something in the middle, like 0, a positive times a negative is a negative. And then something above 1 will have a positive times a positive, which is a positive. So we'll have a max at -3 and a minimum at x equals 1. So again, that's really no different than what we were just doing in that last section. Or 2 sections ago, something like that, earlier this chapter. All right, concavity. What is concavity? Concavity is the curvature of the graph. Is it curving up or is it curving down? So here we have just that same graph. We're going to look at it in the concavity part. So right here, it's curving up. And then, I'll switch colors, it starts curving down. See how it curves down there, and then it curves up again for a little while. And then it'll curve down, curve back up, curve down. This one has an upwards curve all the way to here, and then it curves down. So that's the concavity. The concavity has two options. It can be positive, which makes it concave up, or it can be negative, which makes it concave down. Now, what is the concavity? The concavity, the definition, is it's the rate of change of the rate of change. It's the rate of change of the derivative. So it is the second derivative. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. We look at these the exact same way we look at the increasing and decreasing with the first derivative. We find the zeros, which are the points of inflection. Well, zeros are the points of inflection, kind of like zeros are the maximums and minimums in for a first derivative. It's not always a maximum or minimum, just like this is not always a point of inflection, but it's where they happen. The second derivative needs to change signs from positive to negative or negative to positive, and it's a point of inflection. It can happen when the second derivative is 0 or when the second derivative is undefined. So concavity is the same thing as minimums and maximums, except we use the second derivative instead of the first derivative. That's all it is. Then we have a second derivative test for local extrema as well. This one is, yes, it does work. So here it says if the derivative equals 0, so we don't have any cusps or anything, it's a maximum if the second derivative is negative. Because if you look at one of our maximums here, when it equals 0, second derivative is negative, which means it's concave down, which kind of makes it a maximum. And then same thing if it's the derivative is 0 and the second derivative is positive, it will be a minimum because you're going to have something like that, which makes a minimum point. So next, if we have the graph of the derivative, can we go back to the graph of a function? Yes and no. Yes, we can get the general shape of the function, but no, we won't know exactly where it is. We just kind of take a guess, but again, what we're looking for though is the general shape. So this is f prime of x. We want to find f of x. So what do we know about f of x? We know from -4 to -2, the slope is positive going to 0. So I don't know where I'm starting. It doesn't matter. But starting at -4, going to -2, the slope is 0, or the slope is positive, and then we kind of leveled off to go to 0. And then from -2 to 1, the slope is positive, and we level off to go to 0. So we have to go from 0 slope back to positive, leveling off to 0 again. And then from 1 to 4, it's going from 0 to negative to 0. So we go 0 to negative to 0. That is what this graph could look like. It could be moved up or down as far as starting point. It could be vertically compressed or stretched. Notice in fact that the y-axis is not even labeled here. The x-axis is labeled because that's giving us our guidelines, but the y-axis isn't even labeled. So that's going from the derivative back to the graph. The derivative tells us the slope. What is the graph doing? and you have to go. So just when you thought you kind of had it figured out going from the y value to the slope when you're graphing the derivative, now we're going backwards. So that's just going to mess with you all over again. Motion along a line. So we've done some motion along a line type things before. We're just going to find the derivative, critical points increasing, decreasing, and then the second derivative for the acceleration. And we'll make a sign chart for all of it. So here we have x of t, because it's the x position along a line based on t. It's 2t cubed minus 14t squared plus 22t minus 5. So just a polynomial. We can find the derivative, x prime of t, which would be the velocity of this particle. So the derivative will have 6t squared minus 28t plus 22. And then we'll factor that. Let's find the second derivative as well, though, while we're here. So that'll be a of t. That'll be 12t minus 28. So first, let's start with v of t. 6t squared minus 28t plus 22. That we can factor 2 out. That'll help us a little bit. That'll be 3t squared minus 14t plus 11. And now to factor this, we'll have a 3t and a t. 11's prime, so it has to be 11 and 1. Can we multiply one of them by 3 and add to get 14? Sure we can. That'll be the 1. And they're negative because it has to be negative. So here, t could equal 11 thirds or 1. And both of those are positive. It's important they're positive because t has to be greater than or equal to 0. And now let's do a of t. A of t was just 12t minus 28. So when we set that equal to 0, we can add the 28 over, divide by 12. So t equals 28 twelfths, which we can divide both of those by 4 to get 7 fourths. So we have a line, or we can make a sign chart. I'm going to put the x values on top, and then we'll have the derivative and we'll have the second derivative. So it starts at 0, so we'll start it at 0. And then we'll have 11 thirds, 1, and 7 fourths. Well, 7 fourths is 2 point something. 7 thirds, because when you divide 12 by 4, you get 3, not 4. Why didn't someone stop me and correct me? I mean, come on. I'll forgive you this time. So 7 thirds is 2 point something. 11 thirds is 3 point something. So we're going to go 1, 2 point something, 3 point something. All right, so the derivative will change at 1 and 11 thirds. So like these two will be the same for the derivative because it won't change there. And then the second derivative, these two will be the same because it won't change there. It'll only change at the 7 thirds. We can put it into both categories. We can put it into one and kind of space it. It's kind of up to you. I'm going to just put it into both categories. So I know the derivative will change at 1. So we can put in something less than 1. Like we could put in 0. 0 will work. So we'd have negative 11 and negative 1. Negative times negative is positive. So we'll have a positive here. And then in between 1 and 11 thirds, so say 2. 3 times 2 is 6 minus 11 is negative. 2 minus 1 is positive. So a negative times a positive is going to be negative. So I'm just going to put negative in both of those. And then a number bigger than 11/3 is 10. So that's positive, so it'll be positive. All right, now the second derivative, we need something before 7/3 and something after 7/3. Before 7/3, 0 is kind of nice. 0 minus 28, oh, that's negative. So it'll be negative before 7/3. So it'll be both of these two places is negative. Then after 7/3, we can plug in, say, 10. Well, 10 times 12 is 120 minus 1. Oh, that's positive. So it'll be positive after 7/3. So here we have that it's moving to the right when f prime is positive. So moving right on 0, 1 and 11/3 to infinity. And then left from 1 to 11/3. And then it is the velocity is decreasing. So that could just be getting small, like the velocity is going down, whether that's towards 0 or whether that's further into the negatives from 0 to 7/3. And then the velocity is increasing from 7/3 to infinity. We could look at speeding up and slowing down. Remember, speeding up is when the first and second derivative signs agree. So it'll be speeding up here and here. That's where doing the both sine tables at the same time and on the same scale can help out. So speeding up from 1 to 7/3 and 11/3 to infinity. And then it's slowing when they're different, so 0 to 1 and 7/3 to 11/3. So like from 7/3 to 11/3, it's getting like it's the velocity is increasing, but the velocity is still negative, so it's increasing towards 0, so it's coming closer to a stop. So that's why it's slowing. So that's motion along the line. Again, the first derivative stuff is nothing we haven't done. Putting the second derivative stuff with it is an extra thing, but it's not really an extra new thing. And then a quick review of what we probably know. So things that are differentiable, they're smooth, they're connected, so they don't have, or they're continuous. Graph may go up and down. If the first derivative is positive, the graph rises. If the first derivative is negative, the graph goes down, right? Slopes up, or slopes positive, slopes negative. The second derivative, positive, is concave up. Looks like those. Second derivative is negative, it's concave down. Has kind of that shape. Inflection point is where it changes from concave up to concave down. Now, finding that point on the graph can be a little bit tricky. It sounds kind of silly, but if you have it on paper and you kind of trace it with your pencil, you can feel where it switches from concave up to concave down. It's kind of weird, but you can do that. Then with a little bit of practice, it gets pretty easy. And then when the first derivative changes signs, the graph has either a local maximum or local minimum, depending on which way the signs change. And then these two are the second derivative test for Extrema. If the derivative is 0 and the second derivative is negative, we get a maximum. If the derivative is 0 and the second derivative is positive, we get a minimum. So that is this lesson on how we can connect the derivative and the second derivative to the function itself. Again, there's a little bit of new stuff, but kind of just putting together a bunch of stuff we've already been working on. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.